Hello and welcome. If you enjoy slow, careful explanations of the universe, the kind that take their time with something genuinely strange, consider liking the video and subscribing. It helps this quiet corner of science continue to grow. And before you settle in, take a moment to tell us where you are tonight. Perhaps a bedroom in a city, still faintly humming. A house somewhere rural, nothing outside but field and wind, a small flat in the early hours, the rest of the building already asleep, somewhere warm, a lamp on, the world beyond the window very still. Wherever that place is, you are being pressed into it, right now by gravity. Gently, without interruption. The same force that holds the oceans in their basins and the moon in its long patient orbit is pressing your body minus at this exact moment, softly and firmly into whatever you are lying on. Feel that if you like. The ordinary weight of yourself. Now consider this. A single teaspoon of material from a neutron star would weigh more than 900 Great Pyramids of Giza. 900. The surface gravity of these objects is 100 billion times what you feel right now. A mountain rising from the surface could not grow taller than a few centimeters before that gravity crushed it perfectly flat. And these are not enormous things. They are roughly 12 miles across the width of a small city. They simply outweigh the sun. And this. The gold in a ring on your hand minused if you are wearing one tonight was not forged here or anywhere nearby. It was made in a collision between two neutron stars, approximately 130 million light-years from where you are lying. You are wearing, in a very precise and measurable sense, the debris of the universe's most violent event. So what is a neutron star exactly? What is happening inside something that denser than an atomic nucleus, compressed beyond anything we can produce or even comfortably imagine? What holds it up when gravity of that magnitude is pressing inward from every direction? How does an object 12 miles wide spin 700 times each second, its surface moving at a quarter of the speed of light? What happened on the 27th of December 2004 when something 50,000 light-years away disturbed the very air above our planet in a fifth of a second miceness and was recorded on instruments around the entire globe? And how did a young student in Cambridge in 1967 building a radio telescope by hand across a 4.5-acre field find the first proof these objects were real, hidden in a 5mm squiggle on a paper chart? Those are the questions we will follow tonight, slowly and without urgency. Get comfortable. This will take a while. It is meant to. And here is the quiet promise underneath all of it. As strange as these objects are minus, and they are, genuinely, among the strangest things the cosmos has ever assembled minus. They are not lawless. They are not magic. They are what happens when a handful of very simple rules are pushed to their absolute limit, further than anything on Earth will ever push them. There is a physics to the way matter refuses to be squeezed out of existence, a physics to the way a dying star folds inward and stops, a physics to why the corpse it leaves behind spins and shines and rings like a struck bell. All of it obeys the same handful of principles that govern the weight of your own body against the bed. Nothing you will hear tonight breaks the rules. It only shows you how far the rules can bend. So let go of any need to hold every number in your head. Let the figures wash past the pyramids, the miles, the millions of years. You are not being tested. If your attention drifts and returns and drifts again, That is exactly how this is meant to be heard. We will begin at the very beginning, with a prediction made before anyone had the faintest hope of proving it true. That prediction did not arrive through a telescope, and it did not rise up out of a photographic plate, and it did not follow from any measurement that anyone, anywhere, had yet been able to make. It came instead from two men standing in a room, thinking aloud, at a moment when the object they were describing had no business existing on paper, let alone somewhere out in the dark above your head. There was no evidence for it, there was barely a vocabulary for it, and yet they said it anyway. To feel how audacious that was, you have to step back one small pace further, to a discovery so fresh that the ideas built upon it had scarcely had time to settle. In the year 1932, a physicist named James Chadwick, working in Cambridge in England, found something that had been hiding quietly inside every atom since the beginning of time. Not the electron, which was already known and understood. Not the proton, which was already counted and named. Something else again. A particle carrying no electric charge whatsoever, roughly as heavy as a proton, but neutral, and therefore nearly invisible to the very forces that let us detect most things at all. He called it the neutron. And with that one patient find, the inner architecture of the atom was, for the very first time, more or less complete. Now hold on to how new that was. The neutron had been a confirmed piece of reality for barely 12 months. It was the youngest thing in physics, a particle whose properties were still being sketched in, still being argued over in journals and lecture halls. Most scientists, encountering something that recent, would spend a decade simply learning to trust it. That is the ordinary rhythm of discovery, and there is nothing wrong with it. You find a new brick, and then you spend years turning it over in your hands before you dare to build anything tall. But in December of 1933, at a meeting of the American Physical Society held at Stanford University, in California, two astronomers stood up and did something else entirely. Their names were Walter Baade and Fritz Zwicky, and they were by any measure an unlikely pair to be handing the universe one of its strangest ideas. Baade was careful, meticulous, a watcher of the heavens. Zwicky was brilliant, combative, forever a step ahead of the evidence and unbothered by the fact. Together, they took that year-old particle, the neutron, and they asked a question that almost no one else was asking. What if you did not have just one of them, or a handful of them locked inside a single atom? What if you had a whole star's worth? What if an entire dying star could be squeezed, in its final moments, into something made almost wholly of neutrons, packed together as tightly as they sit inside the nucleus of a single atom, but on the scale of a sun? They knew how it sounded. You can hear the caution in the words they actually chose, words that survive to this day. With all reserve, they wrote, "We advance the view that a supernova represents the transition of an ordinary star into a neutron star, consisting mainly of neutrons, with all reserve." It is a lovely, very British sort of understatement, even from two men who were anything but timid, and it tells you they understood precisely how far out, beyond the edge of the known they had walked. They were not reporting a fact. They were laying down a bet, quietly, with the whole cosmos as the table, and it was not even their only bet that day. In the very same short paper, almost as an aside, they proposed that these same catastrophic stellar explosions, these supernovae, might be the source of the cosmic rays, the high-energy particles that were even then sleeting down through the atmosphere and through the roofs of houses, and through the bodies of everyone alive, unseen and unfelt. Two enormous conjectures then folded into a few pages, a new kind of star and a new origin for a rain of particles falling on the Earth. Either one alone would have been a remarkable thing to guess both in one breath, 1 year after the neutron itself was found, is very nearly reckless. It is the kind of leap that either makes a fool of you or makes you immortal, and there is rarely any way to know in advance which it will be. The following year, in 1934, they set it all down formally in print, in the Proceedings of the National Academy of Sciences, and there it sat. A prediction, fully formed, complete, correct in almost every essential and utterly unprovable. Because here is the trouble they had walked straight into, the trouble that was nobody's fault and everybody's problem. If you take the mass of our sun, and you crush it down until it is made of neutrons touching neutrons, you do not get something large and bright and easy to see. You get something roughly the size of a city. A single dark object, only a dozen or so miles across, sitting somewhere out among the stars, giving off almost no light that anyone in the 1930s had any hope of catching. They had predicted, with astonishing accuracy, an object that their instruments were essentially blind to. They had described a needle and then pointed at a haystack the size of the Milky Way, and so a very particular kind of silence settled over the idea. Not the silence of rejection, exactly. Bayard and Zwicky's neutron star was not laughed out of the room, though it was certainly doubted, and it certainly drifted for a long while at the far margins of respectable opinion. It was more the silence of a promissory note that no one could yet cash. The theory was there. The mathematics could be sharpened. Other physicists over the following years would refine the numbers, would work out how such a star might hold itself up, would calculate how heavy it could be before it collapsed altogether. But none of that was the same as seeing one. A calculation is a hope with good manners. It is not a fact. This is one of the quiet truths about science that we do not often say plainly, and it is worth letting it rest in your mind for a moment as you lie there. The history of understanding is not a tidy march in which evidence arrives first and ideas follow neatly behind. Very often it runs the other way. Very often the idea comes first, whole and strange and years ahead of any means to test it, and then the world simply has to wait, sometimes for a lifetime vinous, for its instruments to grow subtle enough to catch up. The prediction waits in a drawer. The universe carries on exactly as it always has, indifferent to whether anyone has noticed. And the truth of the thing does not depend, in the slightest, on our being ready to receive it. For the neutron star, that wait would stretch on for 33 years. Think of that. A child could have been born in the year that paper was published, grown up, gone grey at the temples, and only then, in middle age, seen the thing confirmed. For a full generation, the neutron star was not an object in the sky. It was an object in the mind, a rumour, a careful sentence in a journal, gathering the particular kind of dust that settles on ideas the world is not yet equipped to believe. And while it waited, the neutron went on doing what it does. It is worth remembering, in the stillness of wherever you are, that the same particle those two men were speculating about is not some remote abstraction confined to exploding stars. There are neutrons inside you right now. They are packed into the nucleus of very nearly every atom that makes up your hand, your ribs, the slow pulse at your wrist, the pillow beneath your head. The carbon, the oxygen, the iron threaded through your blood, all of it is held together at its very centre by these small neutral particles sitting shoulder to shoulder with their charged partners. A neutron star, in the end, is not made of any exotic new material dreamed up for the occasion. It is made of the same stuff you are made of. The only difference, the whole difference, the entire staggering difference, Myers, is how tightly that stuff has been forced together. You are a loose and airy arrangement of it, mostly empty space, held apart by the gentle push of electrons. A neutron star is the same matter with the emptiness driven out. That, in a single thought, is what Barday and Zwicky were reaching for, all those years before anyone could confirm it. Not a new kind of substance, a new kind of squeezing. And the strange, patient beauty of it is that the sky was already full of these objects, while they spoke spinning, cooling, shining faintly in colours no human eye can see, waiting, with a kind of cosmic indifference, for someone on this small blue world to build a machine sensitive enough to hear them. Which brings us slowly to the person who finally did. Because the confirmation, when it came at last, would not arrive as a grand theoretical triumph announced by the men who had earned it. It would come, as these things so often do, as an accident. A small mark, an oddity on a long ribbon of paper, noticed by someone almost no one had thought to watch, in the quiet hours of a cold English autumn, more than 3 decades after the idea was first set down. Her name was Jocelyn Bell, and she was, in the autumn of 1967, a research student at Cambridge, one of only 5 people who had spent the better part of 2 years building a radio telescope with their own hands, not a gleaming silver dish of the kind you might picture. A field. More than 4 acres of ordinary English ground, strung with over 1,000 wooden posts, and a great web of wire slung between them, all of it raised in the wind and the rain by students with mallets and aching shoulders. And when at last it was finished, this strange metal meadow did just one thing. It listened to the sky, and it wrote down everything it heard, in ink, on a long ribbon of paper that unspooled at the rate of roughly 500 meters every single day. Consider what that actually means for a moment before you let it go. Somebody had to read it. All of it. Mile upon mile of faint pen strokes by eye, hunting for anything at all unusual in the endless soft wash of cosmic noise. And it was Jocelyn Bell, running her patient attention down that unspooling paper, who first caught it on the 6th of August 1967, a small scruffy little smudge, a mere scrap of interference, occupying no more than 5 millimeters of the whole enormous chart. A thing so slight that almost any other eye in the world would have slid right past it. She did not let it pass. She noticed, instead, that it returned, night after night from the very same patch of sky, keeping its appointments not with the clock on the wall, but with the slow turning of the stars themselves, which is the first quiet hint that a thing does not belong to this earth. And when they trained the instrument to look more closely, that faint smudge resolved into something close to impossible, a train of pulses sharp and clean, arriving one after another, spaced apart by 1.3373 seconds. Not roughly, not on average. To a precision of about 1 part in a million, steadier than any clock that human hands had yet learnt to build. Think how unsettling that must have felt. A pulse, in the dark, more faithful than a heartbeat, more regular than any metronome, arriving from somewhere far beyond the last of the planets. And so for a little while, and they discussed this seriously and quietly among themselves. They allowed for the strangest possibility of all, that it was a signal, a beacon, something made by someone. They labelled that first source, half in jest and half in real unease, LGM-1, for little green men, and they carried the weight of it through the closing weeks of that year until the 28th of November, when the pulses were pinned down cleanly enough to be sure they were real and natural and not alone. Others soon turned up in other corners of the sky. Whatever this was, the universe was quietly full of it. And here the story turns, in a way that has troubled thoughtful people ever since. When the Nobel Prize in Physics was awarded for this discovery, in 1974, it went to Anthony Hewish, who had supervised the project, and to Martin Ryle, and not to the young woman who had built the array and found the signal on the paper with her own 2 eyes. The astronomer Fred Hoyle said plainly and in public that she had been wronged. Belle Burnell herself bore it all with a remarkable and generous grace, and the world came round to her only slowly. More than 40 years later, in 2018, she was given the Breakthrough Prize in Fundamental Physics, $3 million, and she gave every last penny of it away to fund the studies of young physicists from the sorts of backgrounds that science has too often overlooked. There is something worth holding on to in that as you lie there in the dark. The most precisely ticking object then known to us was found by a person the prizes chose to forget. The cosmos, it seems, does not check anybody's credentials. But once you know that a thing exists, you begin to find uses for it, and it is here that the numbers start to leave the human scale behind altogether. Only a few years after that first discovery, in that same year of 1974, 2 astronomers, Russell Hulse and Joseph Taylor, found a pulsar that was not alone. It was locked in a tight orbit with a second dense companion, the 2 of them wheeling around one another in a fast, close dance. And because the pulses ticked away so faithfully, they could be used as a clock carried on the back of a moving star, a way to time that orbit with an almost cruel exactness. What they measured was this: the orbit was very slowly shrinking. The 2 stars were spiraling inward, bleeding away their energy, and the rate at which they lost it matched, to about 1 part in 1,000, a prediction that Albert Einstein had set down decades before, that such a system ought to be pouring its energy out as ripples in the fabric of space itself. Gravitational waves, unseen, unheard, carrying the motion of dead stars away into the emptiness. It was the first real evidence we ever held that those waves existed at all, and it brought Hulse and Taylor the Nobel Prize in 1993. Now let the scale slide backward in time as well as outward in space, because this next step reaches further into the past than any laboratory ever could. There is a neutron star spinning some 30 times every second, about 6,000 light-years from where you are resting now, in the direction of the stars we long ago named the Bull. We can watch it tonight with our finest instruments, but the death that made it was first seen by human beings almost 1,000 years ago. In the year 1054, astronomers in China and observers across the Arab world carefully wrote down the sudden arrival of a new star in the daytime sky, a thing bright enough to be seen for weeks in broad daylight, and then slowly, over months, fading away. They could not have known what it was. And yet the faint whirling ember left behind at the heart of that ancient fire has been turning, patiently, all through the long centuries since, through every single life that has ever been lived upon this world, and it is turning still, this very moment, as you breathe. And then, on the 17th of August, in the year 2017, everything that had been building across all of these decades seemed to arrive at once. 2 neutron stars in a distant galaxy some 130 million light-years away finished a spiral that had lasted far longer than the Earth has existed, and fell at last into one another. This time we did not merely infer the ripples from a shrinking orbit, we felt them, directly, passing through our instruments, and through the ground beneath them, and through us. And within moments, telescopes across the whole of the world, some 70 of them, swung round toward that single small point of sky. What they found, glowing in the wreckage of that collision, was the forging of gold. Real gold, and platinum, and the heavy elements, made in the fire of 2 dead stars meeting, and scattered outward across the dark. And this is the quiet, crushing truth to carry with you into the deeper stillness ahead. The gold in the ring resting on your finger tonight was not made in any furnace we could ever build, but in the death embrace of 2 of these impossible stars, long ages before the sun itself was ever lit. And so, before we drift on into the deeper dark, it is worth pausing over a smaller question that has been hiding quietly inside the larger one. Before those 2 stars could meet, before they could fall together and forge the gold that rests against your skin tonight, each of them had first to become what it was. Each had to die in a particular way, and to be remade into something the universe builds only rarely, and only under the harshest of conditions. So let us turn that question over, slowly, the way you might turn a smooth stone in your hand without quite looking at it. How does an ordinary star, a great diffuse thing of fire and light, not so terribly unlike our own sun, end its life as one of these? How do you take something vast and luminous and burning, and finish with a corpse no wider than a sleeping city? A corpse that nonetheless outweighs the sun itself? The answer is not a single dramatic stroke, it is a balance, and the slow patient failing of that balance over the whole long life of a star. For a star is, at heart, an argument between 2 opposing forces, an argument that lasts millions or billions of years. On the one side there is gravity, always pulling inward, forever trying to gather the star's enormous weight down toward its own centre. On the other side there is the outward push of fusion, the furnace at the core, where the lightest atoms are pressed together so violently that they merge and release their energy as light and heat and pressure. And for the great middle span of a star's life, these 2 hold each other in a near-perfect stillness. Gravity pulls in, the fire pushes out, and the star simply shines, steady and unremarkable, held aloft by the very heat of its own burning. It is not a stable thing, exactly, but a balanced one, which is a subtler and more fragile kind of peace. The trouble is that the fire is not endless. A star burns through the simplest fuel first, the hydrogen, fusing it into helium across ages so long they blur the mind, and when the hydrogen begins to run thin, the star does not simply go out. It climbs instead to the next rung of the ladder, learning to fuse the helium it made into carbon, and then the carbon into heavier things still, oxygen and neon and silicon, each new fuel harder to ignite than the last, each stage burning faster and more desperately than the one before it. What took the star millions of years at the beginning may, near the end, take only days, and with every step up that ladder, the star is building a heavier and heavier core at its heart, layer upon layer, like the rings of an onion, until it arrives at the one element from which there is no climbing higher. It arrives at iron. Iron is where the accounting turns. Up to that point, every act of fusion has paid its own way, releasing more energy than it costs to force the atoms together, feeding the fire that holds the star open against its own gravity. But iron is the ash at the bottom of the grate. To fuse iron into anything heavier does not release energy at all, it swallows energy, drinks it in. And so at the very moment the star forges a core of iron, the fire that has sustained it for its entire existence stops paying. The furnace, in effect, goes quiet. Not slowly, not gently, but all at once, at the centre, where it matters most. And gravity, which has been waiting with infinite patience through every one of those long ages, is suddenly answered by nothing at all. What follows is one of the most violent events the universe is capable of, and it is astonishing chiefly for how quickly it happens. The iron core, robbed of the outward pressure that held it up, collapses inward upon itself in less than a single second. A ball of matter larger than our whole planet falls in on its own centre in less time than it takes you to draw one slow breath in the dark. It falls until it can fall no further, until the matter itself resists, and then it rebounds. And the rebound tears the outer layers of the star apart in a detonation we call a supernova, an explosion so bright that for a few days a single dying star can outshine billions of its neighbours put together, can briefly rival the light of an entire galaxy. And when that light fades and the wreckage scatters outward into the dark, something is left behind at the centre. Not always the same something. If the surviving heart is very heavy, more than roughly 3 times the mass of the Sun, then not even the matter can hold, and it collapses onward into a black hole, and vanishes from view. But if the remaining core is lighter than that, somewhere between about 1 and 3 times the mass of the Sun, it stops. It holds. And what holds it is the quiet mechanism at the very centre of everything we are speaking of tonight, because here is the strange and beautiful thing. Once the fire is gone, once fusion has fallen silent forever, something else must take up the endless task of resisting gravity, or the star could not exist at all, and that something is not heat, and not burning, and not any force you would meet in ordinary life. It is a rule, a deep rule about how the smallest pieces of matter are allowed to share a space. For when the collapse presses the core to unimaginable density, the electrons and protons are crushed together into neutrons until the whole thing becomes, very nearly, a single enormous mass of neutrons pressed shoulder to shoulder. And neutrons, it turns out, refuse to be crowded. There is a principle woven into the fabric of matter itself, which says that 2 of these particles cannot occupy the same state in the same place at the same time. Pack them close, and they push back, not because they are hot, and not because they repel one another the way like charges do, but simply because the laws of the very small forbid them to be pressed any nearer. This resistance is what holds a neutron star up, not fire, not pressure of the ordinary kind, but the stubborn refusal of matter at its most fundamental level to be told exactly where to be. A dead star, standing against the crushing weight of itself, held open by nothing more than a rule. And what may astonish you most is that human beings guessed all of this, in its essentials, before there was a single scrap of evidence that such an object could exist. The neutron itself, that neutral particle at the heart of every atom, was only discovered in the year 1932 by the physicist James Chadwick. It was brand new. The ink on it was scarcely dry. And yet just 1 year later, in December of 1933, at a meeting of physicists held at Stanford University, two astronomers named Walter Baade and Fritz Zwicky stood up and proposed something almost reckless in its boldness. They suggested that when a great star dies in one of those brilliant explosions, what it leaves behind is a star made almost entirely of these newly discovered neutrons. Their own words, published the following year, carry a lovely, careful humility that I find hard to forget. With all reserve, they wrote, "We advance the view that a supernova represents the transition of an ordinary star into a neutron star, consisting mainly of neutrons. With all reserve." They knew how strange it sounded. They knew they were describing a thing no one had ever seen, built from a particle the world had known for barely a year, and they offered it anyway, quietly, into the record. And they did not stop there. In that same short paper, almost in passing, they proposed that these very supernova explosions might be the source of the mysterious cosmic rays that were forever raining down upon the Earth from deep space. Two enormous conjectures, each of them decades ahead of the instruments that would one day confirm it, folded together into a handful of pages. It is one of the great leaps in the history of science, and it was, for a very long time, exactly that, a leap, a thought without a fact beneath it. For here is the part worth carrying with you as you settle deeper into the quiet. From the moment Baade and Zwicky first spoke those words, the neutron star was not an object. It was an idea. It hung there, in the minds of a few, unproven and unseen, waiting for the world to build the instruments that could reach it. And it would go on waiting, in that curious half-life between imagination and reality, for more than 30 years, while the men who had dreamt it grew old, and the wire and the glass that would finally catch it had not yet been strung across a single field. There is a certain tenderness in that, I think, when you lie still and consider it, that the universe held one of its most extreme secrets in plain view for so long, and that the first human beings to name it correctly did so not by seeing it, but by trusting that the laws they had begun to understand would hold, even in a place none of them would ever touch. The same iron whose exhaustion ends a star and begins this whole cascade is at this very moment moving quietly through your own blood, carried in every red cell, forged long ago in stars that lived and died before the sun was born. You are, in the smallest and most literal way, made partly of the ash that these deaths leave behind. And the rule that holds a neutron star aloft against its own annihilation is the same kind of rule, the same deep refusal of matter to be crowded, that gives the humblest atom in your body its size and its shape as you breathe there in the dark. Consider, then, what happens when that refusal is pushed all the way to its limit. In the ordinary run of things, an atom is mostly empty. There is a tiny dense heart of protons and neutrons at its centre, and around it a wide and sparse haze of electrons, held far out at a distance that seems, by the scale of the particles themselves, almost absurd. And those electrons are kept apart by a rule so quiet and so constant that it is easy to live an entire life without once noticing it. No two of them will ever occupy the same state in the same place at the same moment. Each keeps its own small territory. None will be crowded into the space another already holds. This is not a matter of force exactly, not a pushing away like two magnets turned the wrong way round. It is something stranger and more absolute than that, woven into the fabric of what matter is allowed to be. You do not need its name to feel its work. It is the reason your hand does not sink through the mattress beneath it. It is the reason the floor takes your weight. It is very quietly the reason that anything at all has size. Now hold that thought gently and let a great star die around it. A star, you see, spends the whole of its long life inside a single patient argument, a slow tension between two opposing wishes that never quite resolves. Gravity wishes only to gather. It pulls every part of that enormous mass inward, toward the center, toward a single point, and it never once tires or relents. Against it, the fierce heat of fusion in the core pushes outward, holding the whole vast body open and buoyant, a furnace propping up a cathedral of gas. For millions of years the two stay evenly matched. The star burns, and the burning holds it up, and the holding keeps it burning. It is not stillness, but balance, a stability made entirely of motion. And then, in the deepest heart of the largest stars, the fuel runs down toward its final form. Fusion has been building lighter elements into heavier ones, shell upon shell, hydrogen into helium, helium into carbon and oxygen, on and on through the elements until, at the very center, it arrives at iron. And iron is where the long bargain ends. To fuse iron into anything heavier does not release energy the way every step before it did. It costs energy instead. So the furnace, at its core, simply stops paying. In an instant the outward push is gone, and gravity, which has been waiting with infinite patience through all those millions of years, finally has its way. The iron core collapses. Not over centuries, not over years, but in less than a single second, an inner region larger than our whole planet falls in upon itself and crushes down toward almost nothing. Here is where the little rule of the electrons makes its stand. As the core caves in, the electrons are pressed closer and closer, and for a moment their refusal to share a state holds the collapse at bay, a wall of pure principle against the whole weight of a dying star. But the largest stars fall too hard even for that. The wall gives way, and in the giving way, something quietly astonishing occurs. The electrons are driven into the protons themselves, and where there was once a proton and an electron kept carefully apart, there is now a single neutron, and nothing else. The whole heart of the star converts, particle by particle, into neutrons packed against neutrons, until it is not a ball of atoms at all, but something closer to one single, unimaginable nucleus the size of a mountain range. And now it is the neutron's turn to refuse. The very same rule that governed the electrons governs them too, and their insistence on their own space is what finally catches the fall, halting a collapse that gravity had believed it had already won. The infalling matter strikes that sudden, incompressible core and rebounds, and the rebound tears the outer star apart in a supernova that can, for a few weeks, outshine billions of ordinary suns together. What is left behind, at the very center of all that light, is the thing Barday and Zwicky had dared to name 3 decades before anyone found one. A star made of neutrons, a city-sized ember of pure refusal. The numbers, once you sit with them in the dark, stop being numbers and become something more like vertigo. Take a star between roughly 8 and 20 times the mass of our own sun, and this is how it ends. If the surviving core weighs between about 1 and 3 times the mass of the sun, it settles into a neutron star. Push much past 3, and not even the neutrons can hold, and the whole thing falls onward into a black hole instead. So the entire difference between the two most extreme objects the universe makes comes down to a matter of a few solar masses, decided in the hinge of a single second. And the neutron star itself is barely 20 kilometers across, some 12 miles, no wider than a modest city you could drive across before your tea went cold. Yet folded into that small sphere is as little as 1 1/5, and as much as 2 1/3 times the entire mass of the Sun. The heaviest one we have yet weighed carries more than twice the Sun's mass inside a space you could walk across in an afternoon. To make that human, hold a single teaspoon in your mind, fill it, just once, with the stuff of a neutron star. That one small spoonful would weigh more than 5 trillion kilograms. It would outweigh not one Great Pyramid of Giza, but roughly 900 of them, all of it resting in the bowl of a spoon. The matter is as dense as the nucleus of a single atom, only now that density is spread across a whole city. If you were somehow to take our entire Earth, oceans and mountains and molten core and all, and crush it to this same density, the whole planet would shrink to a ball a little over 300 meters across, small enough to sit quietly inside a large town. And the gravity such a thing commands is beyond any comparison the body knows. At its surface, gravity is not twice or 10 times what pins you to your bed tonight, but something close to 100 billion times as strong. To escape it, you would need to travel faster than half the speed of light. A mountain on a world like this could rise no more than a few centimeters before its own weight pressed it flat and smooth. Nothing stands tall there. Nothing is allowed to. And this is the part I find myself returning to, when the mind grows heavy and the room grows dim. The rule that crushes that mountain flatter than glass, and the rule that holds the neutron star up against its own annihilation, and the rule that keeps you from sinking through the bed beneath you, are all, at their root, the same rule. The same refusal of matter to be crowded, playing out on the scale of a single atom in your fingertip, and on the scale of a star's collapsed heart at once. You are held apart from the floor by the very principle that, in another place, holds a dead sun together. So it is not really a distant thing, this star made of neutrons. It is a familiar law, wearing its most extreme face. And that face, city small and impossibly heavy and hotter at its birth than almost anything the cosmos makes, does not simply lie there in the dark, cooling and quiet. It turns, it spins, and the way it spins is a story of its own. Everything that turns in this universe was turning long before it became the thing it now is. The great star that will one day fail is already turning at the height of its life, wheeling once around in its own slow time across the long ages of its burning, unhurried, the way anything so vast seems almost obliged to move. And when the end finally comes, when the core gives way in less than a single second and falls inward upon itself to a sphere no wider than 20 kilometers, a little over 12 miles from edge to edge, that turning is not lost. It cannot be lost. There is a law at work here, softer spoken than gravity but every bit as unbending, and it is worth resting with for a moment, because it is very nearly the whole secret of what happens next. The law is simply this. Spin, once a thing possesses it, is kept. Physicists give it a weighty name, the conservation of angular momentum, but you have felt the thing itself in your own body without ever needing the words. Sit on a chair that turns freely beneath you. Set yourself gently rotating with your arms held out wide, and then draw those arms slowly in against your chest. You quicken. No one pushes you. No new effort is spent, no hand at your back. The turning you already had simply gathers itself into a smaller space, and in gathering, it speeds up. That is all. It is one of those rare pieces of physics you can perform with your own arms in the dark. Now take that same small truth and let it fall upon something unthinkably larger. Instead of arms drawing inward by a few inches, imagine the entire body of a dying star drawing inward, not by inches, but from something wider than a country, down to the width of a single sleeping city. The spin that star carried patiently across millions of years does not simply vanish into the collapse. It concentrates. It sharpens. A slow rotation that might once have taken weeks to complete is folded inward, and folded again, until the whole star is turning not once in a month, but many times over in a single second. This is not a fanciful picture painted for effect. It is the plain arithmetic of the same law that quickens you in a spinning chair, carried out to a scale no chair could ever reach. And a spinning neutron star, it turns out, does not turn in silence. It carries a beam with it, a narrow jet of radiation flung outward from close to its magnetic poles, anchored to the star and swept around the sky as the star itself rotates, in something like the way a beam fixed to the top of a turning tower sweeps around and around across the dark water below. If that beam happens to fall across the small point in the cosmos where you are lying right now, you receive a pulse. Then the star turns a little further, and the beam swings away, and for a moment there is nothing. Then it comes round again. A pulse. And away. And again. This is the beat hiding inside the word pulsar liner, not a star that flashes, but a steady beam turning past us, over and over, with all the patience of the rotation behind it. It is exactly this beat that left the faint, stubborn, repeating mark on the paper in Cambridge, the anomaly that was almost mistaken for a message from another world. That very first one kept time at roughly 1 1/3 seconds between pulses, and it held that rhythm faithful to 1 part in a million. Steadier, in other words, than any clock that human hands had yet learned to build. A dead star, city-sized, turning in the dark, keeping better time than the finest instrument in any laboratory on Earth. It is worth pausing on that, quietly, before we go on, because it is one of those facts that rearranges something small in the way you see the world. And once astronomers knew what they were listening for, they began to find these beats in an astonishing range of tempos. Some neutron stars are slow and ponderous, turning only once every 30 seconds or so, the beam making a long, lazy sweep of the sky. Others keep a pace that pushes hard against belief. To feel how far that range reaches, it helps to sit for a while with one particular star, perhaps the most watched of them all, the small dense heart of the Crab Nebula. Its story begins on a specific and recorded night, in the year 1054, when astronomers in China and in the Arab world both noted a new star appearing where none had been. A guest star, some of them called it, a visitor that flared into the sky bright enough to be seen in broad daylight, and then, across the following weeks and months, slowly dimmed and was gone. What those careful watchers were witnessing, with no possible way of understanding it, was a supernova, the very death we have been circling all this while, the outward rushing wreckage of a collapse. some 6,000 light-years away, in the direction of the constellation we now call Taurus, a great star had died. And at the centre of the glowing ruin it left behind, there sits its corpse. A neutron star roughly 12 miles across, and it is turning 30 times every second. Let that settle for a breath. Nearly 1,000 years have passed since that light first crossed the sky and reached the eyes of those astronomers, and the object at the heart of it all has not wound down into stillness. It is still spinning 30 full turns in the space of 1 second, at this very moment, tonight, while you lie here in the quiet. It pours energy into the space around it at a rate that is genuinely hard to hold in the mind, something on the order of 100,000 suns a minus, and the fierce sweep of its magnetism builds up electrical potentials in the space nearby of around 10 quadrillion volts. A dead thing, by every ordinary meaning of the word, and yet the least dead-seeming object one could possibly imagine, beating faster than the wings of a hummingbird and blazing brighter than 100,000 of our own sun. And even the crab, at 30 turns a second, is only part way up the ladder. Somewhere far off, buried deep inside a dense and ancient knot of stars, a globular cluster with the plain name Terzan 5-, there spins the fastest neutron star we have yet found anywhere in the sky. It carries a catalogue designation only an astronomer could love, a long string of letters and numerals, so let the name fall away and keep only the number. It turns 716 times in a single second. 716. Try, gently and without straining, to place it in the mind. An object more massive than the sun, wide as a city, whirling around its own axis not once, not 30 times, but 716 times between one beat of your heart and the next. A point riding on its equator is not merely moving quickly. It is travelling at close to a quarter of the speed of light. If you could somehow stand upon that equator and hold on, you would be carried the whole way around the star, a loop of some tens of miles, and returned to where you began, in less than 1.5 thousandths of a second minus. And you would be doing it at a speed at which the very fabric of space and time begins, faintly, to bend. There is something almost violent in that thought, and yet from where you lie, it makes no sound, and casts no light your eyes will ever catch. It simply spins, out there in the dark, keeping a beat so exact that we have taken these stars and used them as clocks, checking our own best instruments against their ticking, listening to that steady rhythm carried across the emptiness. Not a poem about a clock among the truest the universe holds. And here, as the ideas grow heavier and the room grows soft around you, is the quiet turn in the story worth carrying with you towards sleep. All of this, the spin, the beam, the 10 quadrillion volts, the flawless and faultless ticking, arises from two things working together: rotation and magnetism. We have spent our while now on the rotation. We have said the word magnetism only in passing, almost carelessly, as though it were a small detail hung on the edge of the turning. It is not a small detail. Of the two forces braided into these stars, the magnetism is the one that reaches, in its most extreme form, for something further and stranger still, something that can be felt, faintly, across half a galaxy. Think of magnetism as you have always known it, here in the ordinary world that holds your bed and your breathing. The small magnet pinning a note to the door of a refrigerator, the needle of a compass, swinging around and settling toward the north with a kind of quiet patience. A magnetic field is, at its heart, an invisible grain running through space, a direction that magnetized things can feel and are moved to follow. You cannot see it, but you have felt it between finger and thumb, that soft refusal as two magnets are turned the wrong way and push each other apart. The whole of the earth beneath you is one such magnet, a gentle one, its field reaching from pole to pole, steering the compass of the sailor and turning the high polar sky its slow curtain green. That field guides every migrating bird that has ever crossed an ocean at night. And it is faint, almost immeasurably faint. It is unfortunately the only yardstick we have, and it is the one we must now set down and leave behind. An ordinary neutron star, if the word ordinary can be permitted anywhere near such an object, carries a magnetic field somewhere between 10,000 and 100 billion times the strength, measured in units the physicists call Tesla. Hold on to nothing in those numbers except the shape of them. Even at the lower end, this is a magnetism no laboratory that human beings have ever built could hope to sustain for more than the briefest flicker before the apparatus tore itself apart. The compass needle does not merely point near such a star, it is seized. Matter itself is reorganized, atoms drawn out into long thin threads along the lines of force, the ordinary roundness of things forbidden. This is already the strongest magnetism in the known catalogue of things, and it is not, tonight, where we are going. There is a class of neutron star for which even this is only the beginning. We call them magnetars, and they are the reason we came the long way round to magnetism at all. A magnetar carries a field not of 10,000 or a billion, but of something closer to 100 trillion, even a full quadrillion, in the older units the astronomers use, a field a quadrillion times stronger than the gentle one wrapped around the earth and around you now. A quadrillion. 1,000 million million. There is no honest way to feel that number, so let me not pretend to give you one. Let me instead offer a small, strange fact that carries the weight better than the digits can. If you could take one of these stars and bring it to within 100,000 miles of the Earth, closer than the moon has ever been, but still a comfortable gulf of empty space its field alone, reaching silently across that distance, would wipe clean the magnetic strip on every credit card on the planet. Every card, in every wallet, in every drawer, in every city. Not by touching them, not by any violence you could see or hear, simply by being there, and being what it is. That is the field at rest. The field being merely present, doing nothing in particular. And here the story does the thing that neutron stars so often do. It takes something already past the edge of comprehension, and then asks quite calmly what happens when it breaks. Because a magnetic field of that ferocity is not a decoration draped over the star. It is a structure under colossal strain, threaded through the crust and anchored in it, and like anything held under strain, it can slip, it can snap, it can, in a single instant, tear loose and rearrange itself into a lower, more settled shape. And when it does, the energy it has been holding does not fade politely away. It is released. All at once. On the 27th of December, in the year 2004, one such star did precisely this. It is a magnetar, catalogued by astronomers as SGR 1806, and it sits roughly 50,000 light-years from where you are lying most of the way across our own galaxy. So far that the light we see left it while the last ice age still had the northern world in its grip. On that December day, its field let go. In something like 1/5 of a second, less time than it takes you to blink, less time than a single soft breath, that star released more energy than our sun pours out in 250,000 years. Sit with the arithmetic of that gently, without straining after it. 250,000 years of everything the sun does, all its light and all its warmth, every sunrise and every long afternoon across 10,000 human lifetimes, compressed into a flash shorter than a heartbeat from a dead star half a galaxy away. And here is the part that should, I think, arrive quietly and then refuse to leave. That flash was not a rumour, not a faint statistical whisper teased out of the data years later. It was felt. When the wave front of gamma rays and hard radiation crossed the 50,000 light-years of emptiness and washed over the Earth, it struck the upper atmosphere, the ionosphere, that high, thin, electrified shell that sits far above the weather, far above the aircraft, the layer off which we bounce our radio signals, and it disturbed it. Measurably. Instruments around the world registered the shudder. A star so distant that its light is prehistoric reached across the whole width of the galaxy, and for a moment changed the sky directly above every rooftop on Earth, including whatever roof is above you now. If the same star had been not 50,000 light-years away, but merely a few light-years, a neighbour, in cosmic terms the consequences for the fragile chemistry that shields life would not bear calm description. We are spared, entirely, by distance, by nothing else, by the plain good fortune of the enormous dark between us and it. There is one more detail from that December, and it is perhaps the strangest and the softest, and a fitting place to let the intensity begin, at last, to ease. After the great flash had passed, the star did not simply fall silent. For roughly 600 seconds afterward, some 10 quiet minutes, the light coming from it went on trembling, rising and falling in a steady, repeating pattern, close to 50 full cycles keeping time with the star's own known rate of spin. To the physicists watching, this could mean only one thing. The catastrophe had not merely lit the sky, it had shaken the star itself. The entire crust of that neutron star, that impossibly rigid, impossibly dense shell we spoke of before, the strongest solid the universe is known to make, had been struck like a bell, and it was still ringing. A starquake, in the truest sense of the word, the surface of a city-sized object heavier than the sun, oscillating, sounding its single deep note out into the dark, minutes after the blow that rang it. Let that image settle over you as the room settles. A bell the size of a city, forged of matter at the density of an atom's own heart, struck once by the unbinding of a magnetic field beyond all earthly measure, and singing afterward, not to be heard, for there is no air out there to carry a sound, but seen, in the trembling of its light, by patient instruments on a small blue world 50,000 years of light downstream. You began this long night with the simple heaviness of your own body pressing into the mattress, the gentlest possible pull of a gentle little planet. And the same universe that gives you that soft weight also builds these. The same two ingredients, minus a spinning mass, and a magnetic field, minus turned all the way up, past every limit the ordinary world would recognize, until presence alone becomes force, and a flaw in a distant crust can brush the top of your own sky. We have followed the rotation. We have now followed the magnetism to its furthest and most violent expression. Two forces, braided together, driving everything we have described. And yet, for all their extremity, both of these are still only ways of describing what the star does. How it turns, how it flares, how it rings. Neither of them has yet told us what the star truly is, on the inside, beneath the crust, down where the ringing came from. That question waits below us still, quieter than any flare, and it is where the story now slowly begins to turn. So let us turn, gently, and with no need to arrive anywhere in particular. For all the noise we have made so far, the spinning, the flaring, the slow ringing of a broken crust, we have been standing outside the thing, watching it behave. And a behaviour is not the same as a nature. You could describe the way a person walks for a very long time and still never have said a single word about who they are. So now, without hurry, we go inward, past the surface and past the storms, down to the plain and rather difficult question we have been circling all this while. Not what does it do? What, beneath all of it, is this actually made of? Why, held in a grip 100 billion times fiercer than the one that keeps you on your bed, does it not simply fall in on itself and disappear? The first thing to set down softly is its name. We have been calling it a neutron star, and there is a comfort in the word, because a star is a familiar thing, something you have seen every clear night of your life. But nearly every part of that little phrase is a small and forgivable untruth, and undoing them, one at a time, is the quiet work of what remains of tonight. It is not, in any ordinary sense, a star at all. A star, the kind you know, the kind our own sun is a furnace. It is a vast and patient nuclear fire, fusing light elements into heavier ones and pouring the released energy out into the dark as heat and light, steadily, for billions of years. That fire is the whole of what makes a star, and a neutron star has no such fire. Nothing is fusing at its heart. No new energy is being made anywhere inside it. It is not burning. It is only cooling, must very, very slowly, must like an iron bar drawn glowing from a forge and set down in an unlit room. It does shine, and fiercely so. The nearest one to us, that faint and solitary object some 400 light-years away, still holds a surface temperature of around 434,000 Kelvin, a heat beyond any human meaning of the word. But it is not hot because anything within it is alight. It is hot only because it has not yet had the time to grow cold. Not a fire then, an ember. Not a living thing at all, but the still warm memory of one that died, and that quietly sharpens the puzzle rather than easing it, because a true star holds itself open by pushing outward with its own fire against the inward pull of its own tremendous weight. The fire presses out, gravity presses in, and the two hold each other for an age in a kind of long truce. But if the fire is gone, if there is nothing left burning to push, then what in the name of anything is holding this object up? Something must be, or there would be nothing left of it but a wound in space. And the answer to that, perhaps the strangest idea of the whole night, asks us to unlearn something we have believed since we were small children, knocking on a table and finding it firm. Consider your own hand, resting there on the blanket. It feels solid. The blanket feels solid. The two of them do not pass through one another, and this seems the plainest fact in all the world. But it is not quite true, or rather, it is true for a reason entirely unlike the one you would guess. Your hand is not full. Almost none of it is stuff at all. Every single atom within it is, overwhelmingly, empty space. At the very centre of each atom sits a tiny dense knot of matter, the nucleus, and around it, at what is in proportion an enormous distance, there drifts only a thin haze of electrons. If you could grow one atom to the size of a great cathedral, the nucleus at its heart would be no larger than a single grain of salt hanging in the middle of the nave, and all the rest, all that soaring vaulted volume above and around it, nighness, would be very nearly nothing at all. So when your hand rests upon the blanket, no stuff is truly touching any other stuff. Not at all. What you feel as solidity is not matter meeting matter. It is the electric fields of those outermost electrons refusing to overlap, pushing back against one another across all that emptiness. Solidity, in other words, is not fullness. It is a polite and stubborn standoff, conducted almost entirely across void. You have never, in the whole of your life, actually touched a single thing. You have only ever felt the pushing away. Now hold that quiet thought and imagine a pull strong enough to overrule it. A neutron star, more than it is anything else, is the answer to one terrible question. What happens when gravity at last grows strong enough to win that argument? When a great star dies and its own core comes falling inward, the pull becomes so ferocious that the electrons can no longer keep their distance. They are crushed inward, driven down into the protons at the centres of the atoms, and the two of them merge and become neutrons, and the vast, airy, mostly empty architecture of ordinary matter simply nights closes. The void is pressed out of existence. What is left behind is not matter as you have ever known it. It is matter with its emptiness removed, packed as tightly as the inside of a single atomic nucleus, and packed that way not across the tiny width of a nucleus, but across the width of a whole city. This is why that teaspoon weighs what it weighs. Not because the substance is somehow heavy in itself, but because there is so unimaginably much more of it folded into the same small space. Every hollow you carry in every atom of your body, gone, collapsed, filled in. It is the only place in the entire observable universe where matter is crushed to this density across anything larger than the heart of one atom. Everywhere else, from the desk you work at to the farthest gas of the most distant galaxy, matter keeps its emptiness. Only here, in these dead and city-sized cores, is the emptiness taken away. And yet, no Nissen, this is the true marvel of it. Even now, it does not collapse any further. Something still holds. But it is not fire, and it is not heat, and it is not any push you would recognize from the ordinary daylit world. What holds a neutron star open against a gravity 100 billion times crueler than Earth's is not, in the end, a force at all in the usual sense of the word. It is a rule, a law written into the deepest grammar of matter itself, which says, quite simply, that no two neutrons may ever occupy exactly the same state, in exactly the same place, at exactly the same moment. They will not be made identical and crowded together into one. They refuse. And when gravity tries to force them down into that forbidden sameness, they push back. Not because they are repelled by any field or charge, but because the universe does not permit the arrangement in the first place. There is no room in the rulebook for it. Physicists have a name for this refusal. They call it degeneracy pressure, and it is the true and only foundation upon which this whole impossible object stands. Not an ember's warmth holding back the dark, a quantum stubbornness, a law of counting holding back the entire crushing weight of a fallen star. And here perhaps is the small gift hidden inside all of that, the thing to carry with you as you lie there and let your eyes stay closed. That very same law, that identical refusal, is at work inside you at this exact moment. It is the reason your own atoms have any size at all, rather than folding endlessly inward. It is why your hand did not sink straight through the blanket when you laid it down. It is why the floor holds the bed, and the bed holds you, and you are not, even now, falling. The thing that keeps a neutron star from vanishing into a point is the same thing that gives your body its shape and its gentle, ordinary weight. You are held up, tonight, by precisely the law that holds up the densest matter in creation. It is only a difference of degree, only a difference of how hard the universe is being asked to push back. So the neutron star is not really a star, for it makes no light of its own. It is not really solid in any way you have ever meant the word, for solidity was always an illusion draped over emptiness, and here the emptiness itself has been removed, and it is not, in truth, held up by any strength you could point to or name, only by a rule about what may and may not be. And still, for all of that, it is the most rigid, the most enduring, the most faithfully unchanging thing that human beings have ever found anywhere in the sky. To understand how something so strange can also be so steadfast, we have to stop imagining it as one single object and begin, very slowly, to go down through it, layer by layer, from the faintest wisp of air at its outer edge, down and down, toward a center that no instrument has ever read and no theory has yet settled. Begin at the very top, then, with the thinnest thing of all. A neutron star has an atmosphere, and that single word deserves a moment of gentle suspicion, because when you hear it, you are almost certainly picturing the wrong thing. You are picturing the sky. You are picturing the soft, deep envelope of air you were breathing a few minutes ago, the kilometers of it stacked above every rooftop, blue in the day and black at night. Let that picture go. The atmosphere of a neutron star is not a sky, and it is not deep, and it is not, in any ordinary sense, air. On a neutron star like the one buried at the heart of Cassiopeia A-, the wreck of a star that died roughly 340 years ago, some 11,000 light years from where you are lying, Minis. The atmosphere is made of carbon, and it is not kilometers thick, and it is not even meters thick. It is about 4 inches deep, a skin of scorched gas you could measure against the span of a hand, pressed flat against the star by a gravity 100 billion times stronger than the gravity holding you to your bed, and heated at its very top to nearly 2 million degrees. That is the calm outer edge. That is the gentlest part. Go down through it, and the next thing you meet is something the physicists are content to call an ocean, and here again the word is a kindness rather than a description. It is not water. Nothing you would recognize as wet, nothing that could ever ripple or pour, waits beneath that thin carbon air. It is an ocean only in the loosest sense a layer, meters to perhaps tens of meters deep, of matter so hot and so compressed that its electrons have been torn loose from their atoms and set adrift, so that what remains is not a sea of liquid, but a sea of naked charge, held in place not by any shore, but by the sheer downward press of everything above it. You could not swim in it, and you could not drown in it. It is an ocean the way the star is a starness, by courtesy, by analogy, because our small vocabulary of familiar things has to be stretched very thin to cover something it was never built to name. And beneath that ocean, the ground, a crust. Now, of all the misleading words in this quiet descent, that one may be the most misleading of all, because when you hear the word crust, you think of something you could break, the thin, cool skin on the earth, or on a loaf, or on a frozen pond. Something brittle and shallow that gives way the moment you lean on it. Unlearn that here. The crust of a neutron star is a solid, crystalline lattice, and it is not weak, and it is not thin in the way a shell is thin. It is, by the best reckoning we have, the single strongest material anywhere in the known universe, a structure so rigid, so tightly locked together, that it would take forces beyond anything found on Earth to so much as flex it. Not soft, but impossibly hard. Not fragile, but the most unyielding solid that reality is known to permit. And yet, this is the strange grace of the place. It is a solidity, built from the wreckage of atoms crushed shoulder to shoulder, their nuclei pressed so close that they settle into a repeating pattern, like an endless crystal made not of grains of salt, but of the shattered hearts of atoms themselves. Keep going down, past that outer crust, and something begins to happen that has no counterpart in anything you have ever held. The pressure, already beyond imagining, climbs further with every meter, and as it climbs it starts to squeeze the atomic nuclei so hard that they can no longer keep all their neutrons in. The neutrons begin, quietly, to leak. Physicists call it neutron drip, and it is one of the loveliest small phrases in all of science, because it makes something so violent sound almost tender-mice, as though the matter, wrung past its limit, were simply weeping neutrons the way a cloth wrung past its limit weeps water. Below that depth, the picture changes for good. You are no longer in a world of atoms with neutrons tucked safely inside them. You are entering a world of free neutrons, unbound, flowing between the crushed lattice like a tide moving through a reef. And this is where the ordinary bookkeeping of chemistry, this element, that element, this nucleus, that shell, quietly stops applying altogether. There are no elements here anymore. There is only the neutron, in its countless trillions, and the single rule that governs how tightly it may be packed. And what those free neutrons do next is perhaps the most beautiful fact in this whole long night, so let it arrive slowly, and do not strain to hold it. Down here, in the outer core, the neutrons do not merely flow. They become a superfluid, a state of matter so ordered, so utterly free of friction, that it can flow forever without slowing, swirl without ever winding down, move through itself without any resistance at all. It is the same eerie behavior that liquid helium shows in a laboratory when you chill it to within a whisper of absolute zero, a fluid that will creep up the walls of its own container and refuse to stop. But here it is not achieved by cold. Here it is achieved by crushing. And we are not guessing at this from theory alone, comfortable though the theory is. We have watched it begin. That very neutron star inside Cassiopeia A was seen across a mere 10 years of patient observation to cool by 4%, a drop far too sudden and too steep to explain in any ordinary way, and exactly the drop you would expect at the moment a star's core first tips over into superfluidity. An entire change of state, a phase transition in the deepest interior of a dead sun, unfolding not across unimaginable ages, but over a single decade, slow enough, and yet quick enough, that human beings could sit and watch it happen. Not a frozen relic, then, but a thing still changing. Not a corpse, but a body still settling into its own grave. And now you are standing, in the mind's eye, in the only way anyone will ever stand there, at the threshold of the last and deepest region, the inner core. And here I have to be honest with you in a way that the confidence of everything so far has not required, because everything above this point we truly know. The atmosphere, the ocean, the crust, the drip, the superfluid sea, all of that rests on physics we have measured and tested and watched with our own instruments. But at the very centre, where the density climbs past even the density of an atomic nucleus, our knowledge simply runs out. No instrument has ever read that place. No experiment anywhere on Earth has ever made matter so dense, and no theory has yet been able to say, with real certainty, what waits down there. There are names for our guesses, and we will turn them over gently in a little while, for names deserve their moment too, mice. But names are not knowledge, and I would rather not pretend otherwise. It may be that the neutrons themselves hold, packed but whole, all the way down. It may be that they break open into something stranger still. What we can say tonight, and this is the quiet fact worth carrying with you as you drift in this, is that the inner core of a neutron star is the only place in the entire observable universe where matter is squeezed to the density of an atomic nucleus and simply held there, not for a fleeting sliver of a second in some machine, but across a whole vast region, steadily, patiently, for millions upon millions of years. Somewhere above you now, scattered across a sky you cannot see through the ceiling, there are thousands of these hidden furnaces, each one keeping a single secret at its heart that no human being has ever been permitted to read. You do not have to solve it, you only have to let it rest there, softly unresolved, while we begin the slow last descent toward it. So we begin to go down, and the first thing to understand about that descent is that it happens slowly, not in the way a stone falls, but in the way a whole age of the universe passes. Because a neutron star is not only a thing of impossible density and impossible gravity, it is, perhaps more than anything else, a thing of deep time. It keeps time. It is made of time, in a sense we will come to. And to feel your way toward its heart, you have to be willing to let the clock in your own chest slow right down, and to think not in the span of a night or a life, but in the span of ages. Consider, first, how it cools. When a neutron star is born, in that violent second we spoke of much earlier, its interior blazes at a temperature almost beyond naming, something on the order of 100 billion degrees, perhaps 1,000 billion, far hotter than the core of any ordinary star that has ever shone. And its surface, in those first moments, sits above 10 million degrees. That is the beginning. And then, very gently, over a stretch of time that has no real meaning inside a human life, it begins to let that heat go. Not quickly, not in a night, or a century, or even 10,000 years. Over millions upon millions of years, that surface temperature drifts downward, from 10 million degrees towards something nearer 1 million minus, still unimaginably hot by any measure you have ever touched, yet cooling, always cooling, radiating its birth heat quietly into the dark with a patience no living thing could ever keep. There is a neutron star some 400 light years from where you are lying now, one of the very nearest we know of, and its surface, measured with great care, sits today at around 434,000 degrees. It has been cooling for an immensely long time, simply to arrive at a number that would still, in an instant, vaporize anything you could bring anywhere near it. And here is the astonishing part. We can actually watch this cooling as it happens. There is a neutron star we call Cassiopeia A, born from a supernova whose light reached us only about 340 years ago, resting some 11,000 light-years away. We have kept our eyes on it, and in the space of just 10 years minus us a single decade, the merest eye blink against the life of a star minus us its temperature was seen to fall by roughly 4%. That may not sound like a great deal, but to catch a star in the very act of cooling, to measure the change over 10 short years, is a little like watching a mountain visibly lose its height while you stand at its foot. And what that 4% appeared to reveal was something extraordinary stirring deep inside it, the onset, we believe, of superfluidity, the neutrons in its core beginning, all together, to flow without any friction at all. A phase change in the heart of a star, unfolding slowly enough that we could sit and witness it. Now hold that thought, the slowness, the deep time, and set beside it something that seems its perfect opposite, and is not. There is, in the constellation of Taurus, some 6,000 light-years away, a neutron star we call the Crab Pulsar. It is the corpse of a star whose death was seen and written down by human hands by Chinese and Arab astronomers in the year 1054, a sudden new light in the sky, bright enough to be seen in broad daylight. That was nearly 1,000 years ago. 970 years, give or take. And in all the centuries since Misen, while empires rose and fell, while every single person who ever witnessed that light lived and grew old and was forgotten, that little city-sized remnant has gone on spinning 30 times every second, without pause, without rest, keeping its rhythm across the whole of written history, and taking not the slightest notice of any of it. 30 times a second, for 970 years. Think for a moment of how many turns that is. Think of the sheer, patient monotony of the thing, a lighthouse that is never once dimmed, never once faltered, sweeping the same beam through the same dark, second after second, for longer than most of our institutions have existed. And folded quietly inside, that endurance is a small and lovely truth. It is very gradually slowing down. Each year it turns a fraction less quickly than the year before, bleeding its spin away into the light and the fierce field surrounding it. Not stopping, not in any span that you or I could ever wait out, but winding down, like the oldest clock in the universe, so slowly that it will still be turning long after our own sun has died. This is the thing that everyday experience hides from you. In the world you know, the world of the bed beneath you and the still air in the room, fast things are fleeting and slow things are motionless. But a neutron star breaks that rule entirely. It is fast and enduring at once. It can spin hundreds of times a second, and it will keep doing so across an age. And it is, in almost every way that matters, none of the things your senses were built to recognize. It is not solid, though it is harder than any rock you could name. It is not liquid, though its outer layers flow. It is not a gas, not a simple plasma, not a metal, not a stone, not any single category your hands have ever held. Strip away one by one every familiar word we have for what matter can be, and when you have taken them all away, what remains, still there, still turning, is the neutron star. It is defined almost more by everything it is not than by anything we can quite say it is. And then there is the strangest hidden thing of all, the one that lies furthest of all from ordinary experience, and it has to do with time itself. You feel time as something steady, something that simply flows at one unquestioned rate, the same for you and for everyone. But gravity, we have slowly learned, bends time. The stronger the pull, the slower the clock. Here on the surface of the Earth, that effect is so faint, you could live 1,000 lifetimes and never once feel it. On the surface of a neutron star, where gravity is something like 100 billion times what holds you gently to your bed, it is anything but faint. A clock resting there, could any clock survive such a place, would run slow, genuinely, measurably slow, ticking away behind the quiet watch on your wrist. To escape from that surface at all would demand a speed greater than half the speed of light itself. Space is bent so steeply there as almost to defy belief, and where space is bent that far, time drags. To stand near a neutron star, if somehow you ever could, would be to age more slowly than the rest of the universe, the very seconds stretched thin by the weight beneath your feet. So the deep time we have been sinking into is not one time, but many, running at different rates in different places, and a neutron star sits at the very edge of that strangeness. And nowhere is the deep time and the strangeness bound together more beautifully than in a pair of these objects, two dead stars, caught turning around each other. In 1974, two astronomers, Russell Hulse and Joseph Taylor, found exactly that, a pulsar locked in a slow binary dance with another neutron star, the two of them wheeling around a shared center, and as they watched it, patiently, over years, they saw something no one had ever measured before. The orbit was shrinking. Very slightly, very steadily, the two stars were drawing closer together, losing energy somewhere, and the rate at which they lost it matched, to about 1 part in 1,000, precisely the amount that Einstein's equations said should be carried away as ripples in the fabric of space itself. Gravitational waves. The first real evidence, gathered not in any laboratory but out there, from a pair of stellar corpses spiraling together across the dark that space can shiver. It earned them a Nobel Prize in 1993, and it meant that somewhere far off, two neutron stars were falling toward one another across deep time, slowly, inevitably, in a spiral that would take hundreds of millions of years to finally close. Since then we have found something rarer still. A system discovered in the year 2003, two neutron stars orbiting each other in which both, not merely one, reveal themselves as pulsars, both sweeping their beams past us as they circle. Two lighthouses, bound together, each one quietly timing the other. It has become the most demanding test we have ever devised for our understanding of gravity in the one place where gravity is strongest of all, and so far, through every measurement that century-old mathematics has held, out there in a regime its author never lived to see. And this, in the end, is what it means to deepen, to follow the neutron star not only inward through its hidden layers, but outward across time, and to discover that the two directions are somehow the same direction. The colder it grows, the older it is, the slower it spins, the longer it has been spinning. The tighter a pair of them draws together, the nearer they come to the single most violent instant left in their long, quiet lives. Everything about these objects points the same way, down and inward and forward, towards some final resolution that the whole of this slow night has quietly been circling. We have gone down through the crust, and the ocean, and the superfluid sea. We have gone down through the temperatures, and the millions of years. There is one layer left to reach, not a layer of the star now, but the last turn of the descent itself, the place all of this has been so gently falling toward. And we will go there slowly, as we have gone everywhere tonight, in no hurry at all. Consider then what deep time really is, not the few decades you will be given, and not the few thousand years of everything anyone has ever written down, but spans so long that they hollow out the very words we use to measure them. A neutron star does not age the way you age. It does not weather, it does not rust, it does not wear thin at its edges the way a stone in a river is slowly rounded away over 100 human lifetimes. It simply cools and slows across intervals that make the whole recorded history of your species a single held breath. The star we have been descending into has been sitting almost exactly where it is, doing almost exactly what it is doing now, since long before there were any eyes on this planet to notice it. And it will still be there, a little colder, a little slower, long after the last of those eyes has closed. This is the first strangeness of deep time. It is not that these objects are old. It is that our idea of old was never built to hold them, and so we reach for what a neutron star is by naming, quietly, all the things it is not. It is not a solid, though its crust is stronger than any solid you have ever touched. It is not a liquid, though a sea of impossible material moves beneath that crust. It is not a gas, though it wears the thinnest skin of one. It is not hot in the way a fire is hot, nor cold in the way empty space is cold, nor still in the way this dark room is still. It is not matter as your school chemistry described matter, with its tidy shells of electrons and its comfortable acres of empty space, because the emptiness has been crushed away and the electrons pressed into the protons until almost nothing remains but neutrons leaning against neutrons. Every familiar category you might try to hand it, it gently refuses. Not a star anymore in truth, but the ash of one, not alive, and yet turning and cooling and changing, like something that has not quite finished the long work of dying. There is a particular kind of neutron star that makes deep time visible, and it does not sit alone. Sometimes two of them are born from the same collapsing region of space, or drawn together long afterward, and they fall into orbit around one another, two dead cities of the same unthinkable stuff, circling in the dark. In 1974, the very first such pair ever known was found, a binary studied by the astronomers Russell Hulse and Joseph Taylor, and when they watched it, patiently, across years, they noticed something that ordinary experience gives you no way to expect at all. The two stars were falling closer together, not quickly, not in any way you could catch in a single night, or even a single decade, but their orbit was shrinking, tightening by a measured amount, year upon quiet year. Here is the part that everyday life hides from you completely. When two great masses swing around each other, they do not simply keep their orbit forever, the way the neat diagrams suggest. They stir the fabric of space itself. They send out ripples, faint tremors in the very shape of distance and duration, spreading outward at the speed of light, carrying a trickle of energy away with them. Albert Einstein had predicted these ripples decades earlier, from pure mathematics alone, and had half suspected they might be far too faint ever to matter to anyone. And yet here, written into the slow inward spiral of two neutron stars, was their fingerprint. The orbit was shrinking at very nearly the exact rate his equations demanded, agreeing to something like 1 part in 1,000. two dead stars, whispering their motion into the structure of the universe, and the whisper matched the arithmetic almost perfectly. Hulse and Taylor were given the Nobel Prize for it in 1993, and those ripples do not stop at the edge of that distant pair. They keep travelling, outward and outward, thinning as they spread, until at last one of them washes over this small blue world, over the roof above you, over the bed, over your own resting body as you lie there. When it arrives, it stretches you, ever so slightly along one direction, and squeezes you along another, and then it lets you go. You feel nothing. You could never feel it. The change is smaller than the width of a single atom laid across the whole length of your body, a distortion so unimaginably faint that for very nearly 100 years no instrument on Earth was delicate enough to notice it at all. And yet it is real, and it is passing through you even so, and it is the sound a siliners, if a thing so silent can be called a sound minors, of distant matter falling together in the deep. Now hold that image gently as you rest. Two neutron stars, each one heavier than the sun and no wider than a sleeping city, turning around one another in a slow and doomed waltz, and every turn of that waltz spends a little of their energy, and every loss draws them a little nearer. This is deep time made into motion. For hundreds of thousands of years, for millions, they circle and close again, imperceptibly. The gap between them narrowing across spans no single life could ever witness from beginning to end. The physics is patient in a way that nothing in your daily world is patient, and it points always in one direction only. Inward. Closer. Toward the moment when the two of them finally, unavoidably meet. We have since found others, stranger still. In 2003, astronomers uncovered a system in which both stars are pulsars at the same time, both of them sweeping their beams across the Earth, so that the whole delicate falling dance can be timed from both partners at once. It has become one of the most exacting tests of gravity that has ever been performed, and gravity has quietly passed every part of it, which is only another way of saying that the slow fall we have been describing is not a guess and not a story. It is measured. It is happening now, in many places at once, above the very room where you are lying, as steadily and as certainly as the weight that holds you to your bed. And that weight and that fall are the same thing. The force pressing your shoulders down into the mattress tonight is the very same force drawing those two far stars together across the dark as only gentled, spread thin and calm over the ordinary scale of one planet and one person. Everyday life keeps its violence hidden simply by giving you so little of it at a time. But wind that same law up and concentrate it into two collapsed stellar hearts, and it stops being the soft hand that keeps the tea in your cup and becomes the engine of the most extreme event the present-day universe still permits itself. The pairs are falling. They have been falling since before anything human drew breath. And somewhere out there, in this exact moment, one of them is nearer to the end of its fall than it has ever been in all the long ages behind it, closer tonight than yesterday, closer than in all the millions of years before. We are almost at the place that every part of this slow night has been leading toward. Not there yet, but very nearly. And then, in the last thin sliver of that long fall, the waiting quietly ends. For most of their lives together, the two stars circle in a slow and stately way, taking hours to complete a single loop, losing only the faintest breath of energy to the ripples they shed. But gravity, as you have heard tonight, feeds on closeness. The nearer the two draw, the harder they pull, the harder they pull, the faster they wheel, the faster they wheel, the more violently they stir the fabric around them, and the more they stir it, the more energy they pour away into those spreading waves, and so the tighter they fall still. It is a spiral that answers only to itself. In the final seconds it becomes something almost frantic, two collapsed suns, each heavier than the star that warms your world, whirling about their shared centre not a few times an hour now, but hundreds of times each second, closing the last few miles of a gulf they have been crossing since before your species had a name. This is the crescendo the whole slow drama has been bending toward, and it lasts, from beginning to end, about as long as it takes you to draw one slow breath. Then they touch. Consider for a moment what that word can even mean here. Two objects, each roughly the size of a city, each packed to the density of an atomic nucleus, each carrying more mass than the sun, meeting at a fair fraction of the speed of light. There is no gentle contact, no soft folding of one into the other. The matter that behaves like nothing else in the universe, the superfluid cores, the crystalline crust stronger than any steel minus, is torn and flung and swallowed in an instant. Some of it merges into a single briefly spinning heart that may hold together for a heartbeat, or may collapse at once into a black hole. And some of it, a little of it, is thrown outward into the dark, a spray of the densest stuff that exists, suddenly released from the crushing hand that shaped it, unspooling into space at speeds you cannot picture. That thrown material matters more than almost anything else in this story, and we will come back to it. Hold it in mind, and let it wait. Now, none of this needs to be taken on faith, and here is the quiet miracle at the centre of tonight. We have watched it happen. Not modelled it, not merely reasoned toward it, watched it, with our own instruments arriving in real time. It happened on the 17th of August, in the year 2017, though of course it happened out there, 130 million years before that, in a faint galaxy catalogued by astronomers as NGC 4993. The waves it made set out across that unthinkable distance, while the earliest flowers were only beginning to open on a young Earth, and they travelled, patient and unhurried, for the whole of that time, until on an ordinary summer's day they finally reached us. They arrived first as a shiver in space-time itself. Two enormous and exquisitely careful machines, one in the state of Washington and one in Louisiana, joined by a third in Italy. The instruments we build to feel gravitational waves registered a tremor passing through the very ground beneath them, a stretching and squeezing of space so faint that measuring it means detecting a change smaller than the width of a single proton across the length of the detector. And this is the part worth pausing on, lying there tonight. That same wave did not stop at the detectors. It passed through the whole planet, through the rocks and the oceans and the sleeping cities, and through the bodies of everyone alive that day. If you were breathing on the 17th of August, 2017, then in that moment you too were very gently stretched and then squeezed, by less than the breadth of an atom, by the death spiral of two stars in a galaxy you will never see. You felt nothing, but it touched you all the same. The wave did not care that you were only a person in a room. It moved through you exactly as it moved through the mountains. What made this tremor different from the handful caught before it was how long it sang. Earlier detections, the mergers of black holes, a sun nistel, had come and gone in a fleeting instant, a single shudder over almost as soon as it began. This one lingered. It rose in pitch and quickened in rhythm, and carried on for more than 30 times longer than anything they had ever recorded, a slow rising chirp that climbed and climbed as the two stars fell closer, until it swept up out of the range the machines could follow. And because it lasted, it could be traced, and because it could be traced, they knew, within moments, roughly where in the sky to look. Then came the second messenger. Just 1 7/10 of a second after the gravitational wave passed, not quite 2 seconds later, a satellite watching the sky in gamma rays caught a short, sharp burst of the most energetic light there is, coming from the same patch of the heavens. Two entirely different kinds of signal, gravity and light, born of the same event, having raced side by side across 130 million years of empty space, and arriving at our doorstep less than 2 seconds apart. Think gently about what that near simultaneity quietly tells you. It says that ripples in space-time and beams of light travel at very nearly the same speed, a thing physicists had long believed and could now, at last, weigh in their hands. For over a century the idea had lived in the equations. On that August afternoon it walked out of the equations and into the record of what has actually been seen. And here, perhaps, is where the night turns from the story of two stars into the story of everyone who was watching, because the moment those first signals landed, an alert went out, a quiet electronic call passed from observatory to observatory around the turning world, and one after another, telescopes swung toward that small marked region of sky. Instruments on mountaintops in Chile, dishes and mirrors scattered across continents, observatories in orbit high above the weather, something like 70 of them in all, turning their patient eyes to the very same coordinates. Astronomers who had gone home for the evening were called back to their desks. People in a dozen time zones sat up through their own nights, chasing the fading light of a thing that had ended before the first human ever looked up and wondered. And they found it, a new point of light, a soft glow beside that distant galaxy, exactly where the waves had said it would be, the visible afterglow of the collision, brightening and then slowly reddening and dimming over the following days. For the first time in the history of our species, a single event in the deep universe had been felt as a tremor in space, seen as a flash of gamma rays, and watched as a fading star, all at once, by the whole community of people who study the sky. There is a name given to that new way of listening, born fully formed on that day, multi-messenger astronomy. The universe had always been speaking in more than one voice. That night we finally heard several of them together. Now let us return slowly to the material I asked you to hold in mind, a sketch, the spray of dense matter flung outward when the two stars tore each other apart. Because when the astronomers gathered the light of that fading glow and spread it out patiently into its colours to read what the debris was made of, they found something that closes a loop this whole night has been quietly circling. They saw the fingerprints of heavy elements being forged, right there, in the wreckage, in the hours after the merger. Not hydrogen, not the light and common stuff of ordinary stars, but the heavy, precious, complicated atoms, the ones that had puzzled us for generations, the ones that no living star can easily make. In the mundane furnace of a star, fusion builds elements up only so far, and then, as you heard earlier, it stalls at iron and pays no more. Everything heavier than iron has to be built somewhere else, in some rarer and more violent forge by cramming spare neutrons onto atomic nuclei faster than those nuclei can fall apart, a process that needs a flood of free neutrons so dense it scarcely exists anywhere in the universe. And where, in all of creation, might you find a sudden, unimaginable flood of free neutrons, released in an instant into the cooling dark? You have been listening to the answer for hours. You are made partly of its cousins. And it was there, in the glow of two stars that had just destroyed one another, that we finally caught the forge in the act. For it did not begin with a picture, and it did not even begin with light. It began with a tremor in the shape of space itself. On the morning of the 17th of August, in the year 2017, a set of exquisitely patient instruments, the observatories we call LIGO and Virgo, listening not with lenses, but with laser light stretched down long arms of vacuum, felt a faint and rising shiver pass through them. It was a stretching and a squeezing of everything they contained, a rhythmic distortion of distance so small that no measurement made in any earlier century could have caught it, climbing in pitch over long seconds like the last accelerating turn of something falling inward. This was the sound, if you can call it that, of two neutron stars in their final embrace, 130 million light-years away, in a quiet galaxy catalogued only by a number, spiraling closer and closer until they touched and were undone. And here is the first thread drawn tight tonight, the one that reaches back across everything you have heard. The signal lasted longer than any such ripple ever detected before it mined us. More than 30 times longer mined us, because neutron stars, being lighter than black holes, take their time in the ending, and so they sang for the machines a little while before they fell silent. That such a shiver could even be felt was itself the closing of an older promise. You may remember the pulsars from earlier in the night, those precise clocks turning in the dark. Long before anyone heard a merger directly, a single binary pulsar, found in 1974 and known by its catalogue number, had been quietly telling us that gravitational waves must be real. Two dead stars orbiting one another were losing energy, and their orbit was tightening year upon year, at exactly the rate Einstein's equations demanded if the waves were carrying that energy away, matching the prediction to about 1 part in 1,000. It was indirect. It was a slow accountant's proof, tallied over decades. But it meant that when the tremor of the 17th of August arrived, we already believed such tremors could exist. The prediction had been made and half confirmed before the instrument to hear it directly had even been built. Once again, as with so much of this story, the idea arrived first, and the evidence came patiently after. Then came the part that made this event unlike anything before it. About 1 7/10 of a second after the ripple in space passed by, a burst of gamma rays swept over the Earth, from the very same patch of sky, the high, sharp scream of matter torn apart at the moment of merger. And so, the astronomers of the world turned. Roughly 70 observatories, scattered across every continent and lifted above the atmosphere in orbit, swung toward that one small point among the stars, chasing a fading glow. They found it, a new point of light in that distant galaxy, brightening and then reddening over the following days as it cooled. For the first time in the history of our species, a single event in the cosmos had been felt as a shudder in space, heard as a pulse of gamma rays, and seen as ordinary light, all at once, all agreeing. We did not merely detect the collision. We watched the wreckage settle, and in that settling glow, we read the elements as they were being made. The colours of the fading light carried the fingerprints of the heavy atoms forming in the debris, the very process you were considering a moment ago, spare neutrons crammed onto nuclei in the flood, building the periodic table upward past iron in a matter of seconds. The estimates are still uncertain, and honestly told they vary a great deal from one study to the next, but the merger appears to have forged something on the order of 10 times the mass of the entire Earth in gold and platinum alone, and perhaps 16,000 times the mass of the Earth in heavy elements altogether. Gold, platinum, the uranium sleeping in the ground, all of it, or very nearly all of it, born not in the calm hearts of living stars but here, in the annihilation of stars already dead. And so the small mystery that has followed you all evening quietly resolves. The gold that anyone wears tonight, the thin warm band on a finger, the fillings in a tooth is older than the sun and was made in a catastrophe like this one, flung out into a cold dark that eventually gathered itself into a cloud, and a star and a world and a hand. You are, in the most literal accounting, wearing the ash of 2 stars that killed each other before the Earth existed. Let that be the small hope of this final layer. There is a kind of gentleness hidden inside the violence. The universe does not only destroy, it recycles. It takes the most extreme deaths it is capable of, and, in the same instant, it manufactures the rarest and most beautiful stuff we know, and scatters it outward, so that given enough time, some of it becomes precious to a creature that can wonder where it came from. The forge and the ornament are the same event, seen from either end of 130 million years. And yet, sit with it a moment longer, and the comfort cools, the way that distant glow cooled and reddened over its few short nights. Because for even a trace of that gold to exist, 2 whole stars had to be extinguished twice, over first collapsing into neutron stars and supernovae that briefly outshone their galaxies, and then, ages later, spiraling together and destroying what little remained. The ring is not only a treasure, it is a memorial. Every heavy, precious atom you can name is a small tombstone for a star, or for 2. And these forges are rare, rarer than the ordinary deaths that make the lighter elements scattered thin across the vast reaches of space and the long reaches of time, so that a galaxy may wait a very long while between them. The gold is precious in the marketplace, because it is precious in the cosmos. There is only so much, and it took the ending of worlds to make each grain. There is a further unease, too, quieter still, and it is the one that will carry you onward from here. For all that the 17th of August let us feel and hear and see, we still cannot look inside the thing itself. We watched 2 neutron stars merge, and we read the elements in their ashes, and yet the question from the deepest layer remains exactly where we left it. What precisely is the matter at the very centre of such a star, in that innermost core we can neither reach nor reproduce? The merger did not answer it. If anything, it sharpened the question, because the way the 2 stars deformed and rang in their final seconds carries faint clues about how squeezable that matter truly is, clues we are still only beginning to learn to read. We have caught the universe in the act of making gold, and in the same breath we have been reminded of how much at the heart of matter remains sealed away from us. So here we stand, near the end of the physics, with a wedding band on a hand, and 130 million light years of empty dark between that hand and the fire that made it. And perhaps this is the moment to loosen your grip on the numbers altogether, to let the Tesla and the teaspoons and the catalogue names drift out of reach, and to begin, slowly, to step back from the crust and the core, back from the merger and the forge, back far enough to ask not what a neutron star is, but what it means that the universe should contain such things at all. Consider, for a moment, that the question has quietly changed shape beneath us. For most of this long night, we have been asking how a star folds inward in less than the space of a single heartbeat, how a spoonful of matter can carry the weight of 900 pyramids, how a dead sun learns to spin 700 times in a second and keep a rhythm truer than any clock a human hand has ever built. And those are good questions, patient questions, the kind that reward you with numbers and names and the slow satisfaction of a thing understood. But there is another question waiting underneath all of them, softer and harder at once, and it does not ask how at all. It asks why there should be such a thing in the first place. Not how the universe makes a neutron star, but what it tells us about the universe that it can. So let us sit with that for a while, gently, with no need to arrive anywhere. You are lying still. The same gravity that holds you against your bed tonight is the faint tamed cousin of the force that crushed an entire dying sun into a sphere the width of a sleeping city. It is the same law. There is no second gravity kept in reserve for the extreme cases, no special edition written for the stars. The force that gives your body its comfortable heaviness, and the force that flattens mountains on a neutron star to the height of a fingernail, are one and the same, only turned up, and up, and up again, until the familiar becomes unrecognizable. That, perhaps, is the first quiet marvel to carry into sleep. The universe does not keep separate rulebooks for the gentle and the monstrous. It is all one grammar, spoken softly here and screamed out there. And here is where the deeper question begins to press. When you name a neutron star, what exactly have you named? You might feel, and it is a natural thing to feel, that you have pointed at an object, a body, a place, somewhere you could in principle stand, a thing with an inside and an outside, and a surface you could set your hand against. But every step we have taken tonight has quietly eroded that comfortable picture. The surface is not a surface as you know it. The solid is not solid in any sense your fingers would recognize. The atoms have surrendered their separateness, the electrons have been pressed into the protons, the empty space that makes up almost all of the ordinary world, the vast echoing hollowness inside every atom of your own hand, has been squeezed away until nothing remains but nuclear matter touching nuclear matter, edge to edge, all the way down. So perhaps a neutron star is not really a thing at all. Perhaps it is better understood as a place where a set of laws is pushed to its final honest conclusion. Not an object in the universe so much as an answer the universe gives when you ask what happens when gravity is allowed to win almost completely, and something, at the very last instant, pushes back. That pushing back deserves a moment of your quiet attention, because it is one of the strangest and most beautiful facts in all of physics, and it is happening, in a smaller way, inside you right now. What holds a neutron star up? Gravity is 100 billion times stronger there than the force that presses you into your mattress. It should keep collapsing. It should not be able to stop. And yet it does stop, held aloft not by heat, not by fire, not by any fuel still burning the fire went out long ago minus, but by a rule about how the smallest particles are permitted to share a space. Two of these particles cannot occupy the same state at the same time. They refuse. And that refusal, multiplied across every neutron in a city-sized star, generates a pressure that stands against the crushing weight of more than a sun. The same stubborn rule is at work in the atoms of your own body this very second, holding your electrons in their shells, giving your hand its shape, keeping you from simply pouring through the bed and the floor and the ground beneath. The neutron star does not run on some exotic principle imported from the far edges of reality. It runs on the same quiet refusal that is keeping you, right now, from falling through the world. And so we arrive at the tension that this whole night has been circling, and I want to lay it out plainly and then let you hold it loosely, the way you might hold a smooth stone in the dark. Perhaps a neutron star is proof that the universe is, at its foundation, indifferent to us. Here is an object of unimaginable violence, born in an explosion that briefly outshines whole galaxies of stars, magnetized past all reason, spinning, blazing, ringing like a struck bell after its crust cracks. And it cares nothing for us, notices nothing, would extinguish anything that came near without malice or intent, simply because that is what its physics does. There is no comfort to be found in the thing itself. It is not gentle. It is not kind. Perhaps that is the honest reading, and the wonder of it is a cold and clean and impersonal wonder, the wonder of a law obeyed to the letter across 100 million light-years of empty dark. Or perhaps, and this is the other half of the thought, the one I would rather you drift toward as your eyes grow heavy, perhaps the more remarkable thing is not the star's indifference, but its intelligibility. Because here is what should genuinely astonish us, if we let it. A small warm creature on a small wet planet, made of the very elements those dying stars forged, has looked out into the dark, seen a faint squiggle 5 millimeters wide on a strip of paper, and from that thread has unravelled the whole story, the mass, the size, the density, the impossible gravity, the spin, the layers of an interior no eye will ever see. We have never been near one. We never will. The nearest is some 400 light-years away, unreachably far, and yet we know its temperature. We watched another one, tens of thousands of light-years distant, cooled by 4 small percentage points across a single decade, and from that whisper of change we read the birth of a superfluid in its heart. That the universe should contain such extremes is one wonder. That the universe should be knowable, that its most extreme places should leave clues faint enough to fit on a scrap of chart paper, and lawful enough to be decoded by patient minds, that perhaps is the greater one. You do not have to choose between these two readings tonight. That is rather the point. You are allowed to hold both, the indifference and the intelligibility, the coldness of the object and the warmth of the understanding miseness, and to feel no urgency at all to resolve them. This is not a debate you must win before morning. It is simply the shape of a real thing, and real things are almost always larger than the frames we try to press them into. The neutron star is both the most hostile place imaginable and the clearest window we have ever found into the behaviour of matter at its densest and most secretive. It is both a graveyard and a forge. It is the end of one star, and when two of them fall together at last, the beginning of the gold that a stranger somewhere is wearing on their finger. Nothing about it is simple, and nothing about it needs to be simplified for you to rest inside the mystery of it. and I want to hand something back to you now, gently, as the night deepens. For nearly 3 hours you have followed, or half followed, or let the words wash by while your thoughts wandered somewhere kinder minans. And all of that is exactly as it should be. But the meaning you make of any of this was never mine to give you. I can offer you the numbers and the names, the year of the prediction, the night of the discovery, the temperature of a distant cooling star, what those facts amount to, what it feels like to know that the same gravity is in your bones and in the Munster, that the same refusal holds up your hand, and a dead son alikes that is yours. You get to decide whether this is a cold cosmos or a comprehensible one, or, more truly, both at once. No physicist can settle that for you. The instruments measure the star, they do not measure what it means to be a small conscious thing lying awake beneath a sky full of them, quietly astonished, quietly unafraid. So let the choosing be yours, and let it be an easy choosing, the kind you make half asleep. There is no wrong answer waiting to catch you out. There is only a vast and lawful universe, going about its ancient business far above the roof over your head, indifferent to your worries in the most freeing way imaginable. Because the things that keep you awake, the small anxious weights of an ordinary life, do not register at all against the scale of a collapsing star, and there is a strange tenderness in that. You are held by the same laws that hold the extremes, and those laws asked nothing of you tonight except that you notice them, for a while, before you let go. Perhaps then, a neutron star is exactly and only what the arithmetic says it is, a cinder 20 kilometers wide, the spun-down heart of a vanished sun, governed by nothing stranger than gravity, and the stubborn refusal of neutrons to be crowded any closer together. Or perhaps it is something the equations can only point toward, and never quite hold, a place where the plain words you have trusted your whole life quietly come apart, where solid and liquid stop meaning what they mean in the room around you, where a single spoonful carries the weight of nearly 900 great pyramids, and every ordinary category you own simply ceases to apply. Perhaps both of those are true at the very same moment, and the tension between them is not a fault in your understanding, but the honest texture of a universe that is real, and lawful, and still unfinished. You do not have to resolve that tonight. You do not, in truth, ever have to resolve it at all, because the choosing was always going to be yours, and it can be the lightest choosing you have ever made. Not a test, not a thing to get right, just a soft settling of the mind toward wonder rather than toward worry, the way you might turn on a pillow to face the cooler side. And if you drifted off somewhere in the middle of all this, and missed the collapse, and missed the lighthouse turning, and missed the gold Ninus, it is no loss at all, because none of it was ever asking to be memorized. It was only ever asking to be near you for a while. Consider, one last time and very slowly, where all of it sits. Somewhere above the roof over your head, a dead star is turning hundreds of times in every second, and has been turning since long before your grandparents drew breath, and will keep turning long after everyone who will ever remember you is gone. The gold that warms against your skin was forged in a collision so far away that its light spent something near 130 million years crossing the dark just to reach a jeweller's window. The iron riding quietly in your blood was cooked in the belly of a star that died before the sun was born. You are not separate from any of this. You are the same story, told at a gentler temperature the identical physics, merely slowed down and cooled down, and made warm and soft and briefly awake, lying here in the dark, wondering. And that, in the end, is the whole of the comfort I meant to leave you with. Not that the universe is small enough to master before sleep, because it is not, and it never will be, but that it is ordered, that the same handful of laws which hold a neutron star together against a gravity 100 billion times fiercer than the one pressing you into this bed are the laws holding you together too, faithfully, without your asking, without your effort, all night long. There is nothing out there in all that vastness that means you harm. There is only structure and distance and the slow patient turning of things far older than fear. You were never in danger from the scale of it. You were only ever invited to marvel and then to rest. So let the last of the questions go now, the way you let go of a warm cup you no longer need to hold. The star will keep its time without you. The light will keep arriving. The heavy elements will go on being made in the deep places, spoonful by impossible spoonful, whether or not a single mind is awake to know it. Let your breathing lengthen. Let the numbers blur. Let the great, quiet machinery of the cosmos keep its own watch tonight. A dead star is singing above you, in a voice too slow and too old to wake you, and you at last are free to sleep,